Okay, so hope you got energized with coffee and cakes. Let's get energy. Let's expand. Okay, so let me repeat the last words I said before, just before the coffee break, about the another motivation for Starobinsky. Remember again, absolute zero of time article by Meissner. He proposed a third way of understanding things beyond GR in a way to resolve singularities. And the third way is to both Einstein and quantum. So that basically you think both classical and quantum point of view. Surely Stravinsky must have followed that message in formulating an evolution of universe starting close to de Sitter stage. Indeed, before the 1980 paper in 1979, there was already a work by Starobinsky and another person, I forgot his name. I will try to recall. Meanwhile, so they start with the Lagrangian MP square by 2 times some A times R square, let me alpha times R square plus beta times R logarithm of R, something like this. Some scale here, logarithm of R square. Even before this 1980 paper, they did consider a Lagrangian, which is extension of R square, extension of Einstein's general relativity. But they considered R square as a small correction to the Einstein general relativity. So that means, as I explained in the before the coffee break, you can look at a regime when GR is dominant and it is a small effect. And that comes when this in the low curvature regime. So indeed, they were probing the low curvature regime. So there was one of the very influential step in the history of theoretical physics is the finding of so-called conformal anomaly or the trace anomaly. Basically, that's actually one of the starting point, the starting point of Starobinsky in 1980. So GR, G mu nu equal to T mu nu. I put MP equal to 1, the units. And if you start with gravity classical and matter classical, of course, this is classical theory of general relativity. What if you have quantum matter? Okay, that means suppose you start with for example, let's say you start with a classical theory with some scalar field. Let me of this form. This is a scalar field with conformal coupling to gravity. The important aspect of this scalar field is basically if you compute the energy momentum tensor of the scalar field, the trace is 0. You start with a matter which is traceless. Well, you do if you want no scalar field, but let's say vector fields. Still, vector fields give you trace of energy momentum tensor 0. So spinors, you can take any kind of fields with whose trace of energy momentum tensor is 0. But then start to understand that whatever you add is not classical but quantum. And if you do these quantum corrections, one loop quantum corrections to the gravity, Einstein general relativity, you get a universal structure of the trace. If you take the trace of Einstein equations, basically minus Ricci scalar, I'm writing schematically. This is not something we are deriving it. So this is to tell you, if you read the 1980 Stravinsky paper, the starting point is not R plus R square Lagrangian, but although what was computed is exactly R plus R square. So we want to explain you a bit so that you can go through the paper and reproduce some of the things. So The structure of this trace of energy momentum tensor is basically alpha times Gauss-Bonnet, some beta times Wild square plus gamma times box R. This is a result you get. You take GR and quantum matter and compute one loop corrections to of one loop correction to the graviton propagator due to matter fields. And you get a universal structure. And the important point is this universal structure has a term box R. Suppose you neglect these pieces. While let's say if you talk about FLRW spacetimes, while is zero, and you neglect Gauss-Bonnet, then you end up with a equation which is relates the box, the D'Alembert times acting on R is proportional to R. Maybe they, yeah. And so in the trace anomaly calculations, this term can be determined precisely depending on the number of fields you integrate. This term can be determined precisely, but this is a free term. And this term is exactly what you get if you start with a classical Lagrangian R plus R square. So there are two messages here. Suppose you start with this theory, which is just a modification of GR by adding R square term. Okay. This is a huge modification, right? This term, as I already explained you. But on the other way, you start with GR and quantum matter already tells you the same structure comes as a quantum correction. That means basically, indeed, this term is coefficient is unconstrained, and you can add a classical addition to the Einstein gravity, which is a kind of message you get from the quantum correction. So this was the initial motivation, and in the Starobinsky's original paper, he takes this coefficient to be such that F0 is huge. Hope this clears the doubts. And there is a good reference for this. There is a trace anomaly driven inflation by Hawking and Hertog, where this motivation was clearly explained. Why R plus R square is R square term is a modification of gravity that is suggested by standard QFP calculations. And there is another point of view. Look, we know, I already explained you, if you want to get something departing from GR completely, you need to add a new degree of freedom, which is not just coming from a small perturbation. So if you otherwise you still get close to GR and you end up with singularities and you end up with all the evolutions which will not explain you actual universe. So the logic is to depart way away from GR, and this requires adding a new degree of freedom. So this is the message from all these developments. Okay. So if you take that Lagrangian, and these are the equations of motion. As you see, if you put F0 equal to 0, you recover GR equations. Quite easy. So I wrote it in this specific form. If you look at this, for example, say de Sitter stage, in the de Sitter stage, R mu is R by 4 delta mu. So basically in the de Sitter stage, if you are close to de Sitter stage, this term is 0. So let's take the trace of this equation, which gives you, as I said, like I keep writing MP square sometimes just to keep track of dimensions. So the trace is R, and this is completely traceless. And then this one is minus 2 F0 box minus 4 box R. And let's take no matter. You are taking a gravity theory without any matter, but with higher curvature modifications. What do you get? MP square R minus plus 6 F0 box R equal to 0. Again, if you put F0 equal to 0, you get R equal to 0. You have no dynamics for the Ricci scalar. But due to the presence of this term, you have a dynamics to the Ricci scalar. So that means we need to explore what is giving us away from VR. If you work out, if you plug in this, what is F0 in that convention, so you see this explains why the 6 factor is there, which is also Luca put it is in his lecture in explaining quadratic gravity. So mp square r 6f0 is mp square by 6m square box r equal to 0. This gives you box r equal to m square r. So a differential operator acting on Ricci scalar giving us Ricci scalar. This is like an eigenvalue equation. Yeah. Ah, it is outside. Thanks. Yeah. Everywhere outside. Perfect. Yeah. Not a perfect correlation between my hand and my brain. Thanks for correcting me. So you see, this is eigenvalue equation, and this is gives you some dynamics to the Ricci scalar. Okay. Well, how do we solve this equation? First of all, we are taking a theory in vacuum. So T mu nu is 0. Okay. And if you look at this one, the Ricci scalar, remember the Ricci scalar is for the flat FLRW metric. 12h square plus 6h dot. Well, you can ask the question, why do I start with flat? I will explain a bit later, but let me start with the flat FLRW geometry. And there is already one derivative here. There are box operator for the flat FLRW is basically minus 3h dt. Of course, you have spatial derivatives, but I'm taking FLRW, which is scalar is function of time, so no spatial derivatives important for to solve this equation. And you look at it, there are two derivatives acting on h. That means you get three h three dots. That means his third order differential equation. It makes it complicated. This is a complicated equation. Mathematical does not solve it. It completely fails. But humans are clever than computers, so we can solve it analytically, but with a different trick. We don't hit directly the trace equation. We hit the 0, 0 equation. Let me erase this. So remember, we already wrote in the previous lecture all the quantities, G mu nu, Ricci scalar, R mu nu. You just need to plug everything and get 0, 0 equation. I'm writing the results. I believe it's trivial. You just substitute everything and R0, 0 and Ricci scalar. R0, 0 is then you end up with a 0, 0 equation, 3h square. Again, I drop mp equal to 1 here. So uh, r by 2 m square h dot minus h r dot by m square equal to 0. This is 0, 0 equation. Okay. You see, in this equation, there are two time derivatives acting on Ricci scalar. And this equation, you just have one time derivative. So that means it's one order less, easy to solve. Because at the end of the day, you solve for the scale factor. There's only one thing. Whatever you solve, you get some solution which should satisfy all the equations. But still, it is a second order differential equation. Again, Mathematica fails to solve it. We haven't developed much the Mathematica. So yes, but then this was solved very elegantly by Starobinsky a long time ago by rewriting this equation as a first order differential equation. How to do that? Well, you just do a variable, you define different variables. Let me write the variables and I write the equation, then we can check. This exactly gives the same equation above. Okay. Let me define some x, h power 3 by 2, and y, h dot by 2 times square root of h. You make these two definitions, and you can easily write dt as dx by 3x power 2 by 3y. It looks complicated for you, but actually it's not. We define this, and you take because h is function of time, so you get dx by dt, and then rewrite it in terms of this. Then this equation gets transformed a first order differential equation so you can verify this. Uh, so dy by dx is dy by dt, dt by dx, dy by dt, you can compute easily, and then it gives you h double dot minus 3 h dot. I'm just writing the result I calculated. You can verify if I'm correct or not. But what you get straightforwardly is this one. Sorry. Yeah. Basically, I'm writing this equation in this form. So on the left-hand side, I write what is dy by dx. And the dy by dx is equal to this one. And this is equal to minus m squared by 6h dot, because x power 1 by 3, if you do it, it is square root of h. Multiply x power 1 by 3 is square root of h. So x power 1 by 3 is y is this one. So basically h dot by 2. Yeah, then you get the 6 factor. Okay. Now you can verify that this equation is exactly same as the 0, 0 equation. Now, as I explained before, the starting point of the universe something very close to de Sitter. How do you make something very close to de Sitter? Is basically when this term is negligible. That means your Ricci scalar is 12h square. If h dot is small, indeed you satisfy the condition only when h dot is small. So when h dot is small, that means y is very close to 0, right? So look at this equation. Y is very close to 0. And dy by dx is basically, it's a variation of h dot, roughly. And it is very close to 0 too. So basically, the first order solution you get here. Let me erase this part. The reason I'm going in very detail because the solution for this equation is written in the literature in a wrong way. So I want to correct that. So the first order solution is basically you equate dy by dx to be 0. Let me call it as, well, not the first order, well, let's say 0th order solution. So let's go start from 0. 0th order solution is this 0. That means y naught is minus m square by 12 x power 1 by 3. It just comes so easily. This is 0. So y is exactly, if you solve this equation, y naught, you get a solution. The 0th order solution, y naught is minus m square by 12 x power 1 by 3. Okay, fine. Let's see the next order solution. Yeah. Origin is we basically, if you look at the left hand side, if you are close to de Sitter, that means your variation of parameter is extremely small. It's a condition. So where you are, what is the evolution of the universe if you are starting very close to the de Sitter? So we start 0th order solution is close as possible. So the dy by dx is approximately 0. Then this term is 0, and then you get a y. It's an assumption that to see to solve the equation close to the symmetry, and then start to understand how you can deviate from the symmetry. Yeah. H dot is approximately 0. If you have de Sitter, yes, H dot is exactly 0. This one. Yeah, H dot is close to 0. Basically, when H dot is close to 0, you have y is close to 0. Y is very small. So, well, naively, if you look at this way, but if you look at the space of it, and if you start evolution with y close to 0, you get the curve which is almost flat. So it's you can do the phase plot of this. Yeah. And the question. Okay. Let's see the next order solution. What is the next order solution? You say y is y naught plus y1. So we go first order, dy by dx is approximately 0, but then next order, okay, some another correction to this 0th order solution. Well, you repeat the same game. So you substitute this in the equation, dy by dx approximately dy naught by dx plus dy1 by dx. And you demand that again close to 0. And you want to compute what? Right? So recursive, exactly. So recursive, we're close to it's like a phase space, right? So you basically have dy by dx close to 0, and you get a 0th order solution. When you solve it, you get a 0th order solution. Why not? And you plug in back with 0th order plus additional correction to the next order, and you plug in back in the same equation, and and then try to find out what is exactly the next correction coming from the perturbation. You try to solving it in a recursive method. So that's standard. So you may ask, okay, this is just math. Why are you solving it? There is a message at the end. So uh, this is it. And if you basically, when you write dy by dx, so on the left hand side, what does it mean? It's m square by 12x power 1 by 3 y naught plus y1, right? Because your new solution is y equal to y naught plus y1. So you need to look at this equation. And of course, then there is a factor of 1 because you are close to y equal to 0. Indeed, you can neglect the 1, factor 1. And this is approximately equal to this one, right? Because you see this one, let me write it precisely. So dy by dx is equal to 0. This means basically minus m square by 12x or 1 by 3 y naught plus y1. So, but you know y naught from this solution, and you substitute it here, okay? And you equate everything to 0. And then you do an expansion in y1, small y1, and compute y1. Is that procedure clear? Yeah.
You're throwing away one.
Y is close to 1, so this term is anyway huge compared to 1.
But then it's not 0. That's the whole point, right?
No, this is not 0. Okay, let me repeat it. Yeah, let me repeat it. Maybe let me repeat it. Step number 1, 0th order. So which gives you some y naught, which is already written there, written somewhere, is here. Yeah. Then you assume that your solution is y1. Plug in back in that equation, differential equation. Okay. Of course, you can include y minus 1. It doesn't matter. Okay. Then this one is dy naught by dx plus dy1 by dx equal to the whole thing. And you know y naught, you can differentiate it with respect to x and substitute it here. And then you get dy1 by dx equal to something. And then you equate dy1 by dx is also small, it is 0. Then because you do Taylor expansion, so when you Taylor expand it, the next term will be you do Taylor expansion of this, basically you get 2 terms. Okay. So you solve this equation and you get a solution for y1, which is, well, if you plug in this equation turns out to be minus m square by 36 x power 4 by 3, because this is derivative of y naught plus m square y1 by 12 x power 1 by 3 y naught square, which you equate it to 0, gives you y1 y naught by 3 x cube. So your full solution now, next order in perturbation theory will be basically, let me write somewhere here. Y equal to minus m square by 12 x power 1 by 3, sorry, which is the 0th order solution, plus y naught. Well, this is basically the y naught plus y1, right? So y minus, okay. 3 into, so that means 36. So you get the next order solution, which goes inverse in x cube. That means in the large x, your correction remains small. What does this give you? This gives you a solution for h dot. What is h dot at the end? H dot is basically 2x power 1 by 3 y. And you plug in the full solution, y naught plus y1, and you end up with minus m square by 6 plus m square by 216 x power 4 by 3. So this is your h dot. But still, we are not yet done, right? But at the end, what we want to know? We want to know the scale factor. Okay, how the universe expands. So this is not the end of the story. Remember, there is this relation. If you solve this relation, you integrate this relation by substituting this there. Okay. And if you do the, like, it's quite straightforward procedure, it will give you, let's put it this way. Let me solve this equation with the zeroth order thing. Okay. Y0. Let me plug in y0 here. And if you plug in that, you basically integrate some time to time, next time, some initial time to the final time. So why not? If you basically, wait a second, sorry. You have to integrate this relation, dt equal to integral dx three x power 2 by 3 y naught. Remember, the y naught is some function of x. Okay. And if you do this integration and assume that you basically have some initial value of h, or maybe you can even impose initial condition to be 0, or just do the definite integration. So it doesn't really matter. So you get some delta t 6 let's say some time ts minus t. Okay, some delta t. So you start with some time and then some evolution in a time interval ts minus t. Okay, so you get this relation. And if you plug in back, this gives you Hubble parameter as a function of time, right? So if you plug in back in this relation, because here in the zeroth order solution, you get some delta t in this one, and then you can plug in back in the other relations and then compute basically the scale factor. So at the end of the day, you want to obtain a scale factor. And after all this lengthy procedure, you get a scale factor. I will explain the reason why we are going through all these things. Okay. So you get a solution for a scale factor. So what did we do? We took R plus R square model. It is difficult to solve the zero trace equation, but from the trace equation, you understand that Ricci scalar got dynamics. And so we go to 0, 0 equation. It's still a second order differential equation, and you turn it into a first order by defining variables, and then you get a like a in this new variable is the first order differential equation. You can also study fixed points and everything. The fixed point is basically close to de Sitter, and you perturbatively with the recursive method solve and get a solution. And you plot this solution, you indeed get an exponential growth. And the TS is a time which is basically TS much greater than T. In this regime, when T is much greater than, yeah, in this regime, that means in that small time scale, TS is some later time. In the basically, maybe it's good to write this way. So T less than TS, you get an evolution which is very close to de Sitter. So this is an exponential expansion. The point is the following. If you look at this, I mean, it's a bit more complicated picture of evolution than what you usually see, exponential of HT, close to exponential of HT, you know. So this is much more detailed expression of how the universe expand. So why do we write this? The point is the following. In the literature, for example, in the Mukhanov, Brandenberger review, the solution to the R plus R square equation in the de Sitter approximation is written like this. It's almost looks the same, but instead of this power, you get this power. This is not correct because if you go to the next order, you get a correct equation. Because of this mistake, it's sometime in the literature, this solution is considered because suppose you remember that R plus R square, M square R, this is a trace equation of R plus R square theory. Suppose if you add a cosmological constant, this particular solution turns out to be exact solution of this one with a negative cosmological constant. So this solution is wrong because this solution will exponentially expand, then it will turn around completely and it will collapse. The universe would collapse if this is the kind of evolution. So, well, you get this wrong result because you do not do the next order in expansion. So it's important always to look at very meticulously, even those are small things, but they carry a great value. So the point is, yeah. No, because this is a solution valid only in this regime. So we did the approximation de Sitter it's in the close to de Sitter stage. So you should not see it as a singularity because you solved it in a specific approximation. And if you look at this equation, it gives you exponential expansion of the universe. And then what happens afterwards? That's natural question, right? Remember that this is the regime we are exploring. What happens afterwards is exit of this regime towards this regime. That's where GR plays a role. Okay, then you solve the system when R square term is dominant. Then you solve the system when GR is dominant. And if you solve the GR dominated regime, basically solutions exist in the review by Antonio De Felici and Shinji Sujikawa. So that's why I'm not repeating this. But if you solve in this approximation, you get a solution. A is some a1 t power 2/3 1 plus 1 over mt sine mt. But you can read physics from here. If you have pure GR, we know the matter-dominated solution is t power 2/3. There is no this term. But now you have, in the initial stage, you have an exponentially growing expansion given by this. And then it exits that phase, and that phase exits, and the universe enters into a regime of matter-dominated with small oscillation. The scale factor has some small oscillation. Then you ask a question, come on. You start with r plus r square, and you just solve the equations. And then I'm talking matter domination. Where is the matter here? The matter is the additional degree of freedom, which is in r square term. In the beginning, when it is dominant, it inflates the universe. And when you enter the matter domination, it will cause ripples in the space-time, small ripples, and these produce particles. This is in the later 1981 excellent article by Starobinsky. It's a very good lecture notes, actually. So which has contained all the details. When you make a transition from this stage to this stage, so you completely evolve from a geometry which is close to de Sitter, close to symmetry, and you go to this stage, which is matter dominated with small oscillations. And that's where you produce particles, which is called the gravitational particle production. It's a phenomena which was known in 72 by Zeldovich and Stravinsky. How do you do it? You study quantum field theory. You write your quantum fields. What are quantum fields here? Here we are just studying background, right? We have a gravity theory. We start with FLRW metric, where there is a scale factor. And we start the universe close to de Sitter. But then you study fluctuations, metric fluctuations. That means you study fluctuations in the geometry. And these fluctuations evolve. What are these fluctuations? You have two kinds of fluctuations. One is there is an additional degree of freedom. This additional degree of freedom cause the metric scalar fluctuations, which are dynamical. In GR, you do not have a scalar field. It's not dynamical. Basically, just your Newtonian potential, and you have gravitational waves. But you have r plus r square. You have an additional degree of freedom, metric degree of freedom, and in the evolution of universe, you start with this space, and the ripples are created by all the degrees of freedom of the theory. Okay, and these ripples, these are produce all the inhomogeneities and anisotropies. So, well, when this stage, they get produced all the time, right? So they get produced during inflation. And then, so all the way when you have a transition from the most symmetric stage to this stage, which is less symmetric stage, of course, then you get particles because you make a transition from one vacuum to another vacuum. This is what the work of Bogoliubov, in the name of Bogoliubov coefficients. Basically, when you have a transition from one spacetime to another spacetime, you get particle production. And here, you do not have particles here. Here, during inflation, you have this field, which is the new degree of freedom, which is dominant. It is everywhere in the spacetime. And expanding it, so the pushing, causing an accelerated expansion. And when it exits, it's the same degree of freedom acts like a matter. And that's why you have this kind of stage. And this matter called scalaron, and this will later decay into all the ultra light particles we know in nature. So what this produces is an accelerated expansion. Look at this one. Of course, it is intuitive to think exponential of ht, but when you look at the actual calculation, it is quite messier, but it is an exponential expansion with an exit towards a regime dictated by GR, but then some small oscillations, and this gives the whole degrees of freedom in nature, whatever standard model or dark matter, we don't know about that, but so this is actually called the reheating in the standard terms. So here the goal is to give the geometric picture completely. I hope this part is completely clear. Any questions?
When you insisted so much that you have to go to the next order to get the right code up front, and you go to the next order to check the
It is done very recently by Verno and collaborators. If I'm, it is stable. Yeah, it is stable. So this was shown. Yeah. So fine. By the way, I'm repeating a lot of things here, repeating again and again the same point, but it's important. When you have this equation, a trivial observation tells you that R equal to constant is not a solution. So we are starting with R approximately constant, but then it deviates and goes to some known evolution. So that's called unstable de Sitter or quasi de Sitter, which is inflation. The term used by Alan Guth for which has come with the observational motivation of explaining the scale invariant spectra, which is often called the horizon problem. And then there is a flatness problem. Well, the problem is basically why the universe is flat. Uh, if you have exponential expansion, if you start with the curvature of space-time, it gets diluted as the universe accelerates. So basically, remember that your Ricci scalar is 12 h square plus 6 h dot. If you have the curvature, spatial curvature, it looks like this. And as the scale factor grows, this term gets diluted, and this is what can explain the flatness. But there is another point of view from observations. Okay, well, universe is absolutely flat. It's flat. What is the problem? Right? It's not a problem. Well, uh, there are other reasons to think of why the closed Dister space with the closed FLRW coordinates. Remember, it gives a kind of a contraction and expansion, but still de Sitter. Now, if you really solve the whole theory with positive spatial curvature, there may be a non-singular solution, and surely this is a currently people are exploring this. For example, there's a recent paper by Mueller and Toporensky. They found a solution in Jordan frame, which is a bounce and asymptote to Starobinsky like inflation. So the point is, yeah. 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 Uh, yeah, it's true. It's no, analytically, it's not possible. So, but I did plot the numerical one, which I will include in the lecture notes. Basically, you get a solution in the logarithmic scale. So you get a solution which goes kind of like this. So you have exponential growth, and then it goes kind of like not polynomial, monomial way, which is basically the t power 2/3. So you get a solution which is interpolates between these two regimes, and yeah, during the transition is quite rapid. And what happens in this rapid transition? Well, it's something again active research which has emerged only in recent years. So the people started to understand what happens to these fluctuations at very small scales during this rapid transition and during this oscillatory regime. Because you see, what oscillates here is the geometry that oscillates, but this oscillation is created by the degree of freedom, new degree of freedom, which you will see shortly. Shall we take a 2 minutes break? before I go to the perturbations? Yeah. So I think good. I didn't hope to achieve perturbations in this lecture, but yeah, we'll start in 2 minutes. The solution is clear. Okay. Okay. It's recursive relation, but yeah. No. Yeah. Huh? Scalar. Scale round. Yeah. 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 It behaves like a particle because it's like a small oscillation locally, like a ripples in spacetime. You can interpret it as a particle, but during inflation you cannot interpret it as a particle. It's a field. It's a part of geometry. So it's a no, no.
Where's the degree of freedom which is which then corresponds to the you mentioned that Scattering comes from the additional degree of freedom.
Which is coming from the R square F0. Yeah. Yeah.
Where's
I'll show you that.
okay.
I'll show. So far, what is degree of freedom in GR? You start with a geometry and look at the fluctuation. That fluctuation is what degree of freedom is, right? And when you do the fluctuations around this FLRW geometry, and you see your Bardeen potentials, they are not potentials; they are dynamical fields. So that's what you see, the degree of freedom. Yeah, yeah.
How does it how does it interact with the other standard molecules or particles? Because
Uh,
actually, even with matter term, it's not clear how they interact.
okay, I will answer that question. So it-
Perturbation.
yes, it's exactly because
Perturbation. Then go
your
to the interaction with all
exactly. Your metric has a new degree of freedom. Your metric has a new degree of freedom. So because this new degree of freedom, wherever you put the metric, even the minimal coupling, you are coupling your geometrical degree of freedom with matter. Yeah, so that's where the interaction comes, and you can do it in with a conformal transformation, but that's
physically that absolutely makes
yeah,
sense.
yeah,
Mathematically, if I just look at the action,
yeah,
another LM matter term
yeah,
in the bracket,
yeah.
then it looks to me like the quadratic our perturbation is lives very unaffected from the
No, no, it is affected because when you do the because you see that Bardeen potentials are dynamical. So then when you do the fluctuations, may do fluctuations in everywhere, matter, geometry, and everywhere. And when you look at those fluctuations, because there is square root of minus g, and also the minimal coupling, the kinetic term. Your square root of minus g, you should not think it like in GR. So now you have your trace of h mu nu does have dynamics physically, yeah, but I will show you. Let me show. When we work out perturbations, we will try to understand. We will understand that. Yeah. Yeah. Okay. So fluctuations. How do we understand metric fluctuations in this theory? So there is a question how matter can couple to this new degree of freedom and how the particle production happens. I will try to comment on it a bit later. So once we first understand the metric fluctuations, but I will not do that in detail. So how the particle production happens and all, but I can give you more references in the lecture notes. So what is the space time? You start with FLRW. There is a better way to write this space time in a different time, which is called the conformal time. You would do this definition, redefinition of time, and then this metric looks conformal to Minkowski. Of course, it's not Minkowski's finite, it's conformal time. This is nice way to see it because what we want to do always is to do the replication from known physics to unknown physics. So this way of writing helps us to understand and make a connection to what we know. So when we study the fluctuations around this metric, we can do these fluctuations in the scalar, vector, and tensor part because we are studying linearized fluctuations, and at the linearized level, all the degrees of freedom decouple. So we look into only the scalar part. And the scalar fluctuations usually written as this. I am skipping there are basically, you can write into 4 scalars, but you can remove the 2 scalars by diffeomorphism invariance. So basically, so these are called Bardeen potentials, so which basically a remnant after you throw away the gauge degree of freedom. So then you end up with Bardeen potentials. This is also often called the Newtonian gauge. And in GR, if you just study GR and study fluctuations of metric in GR, let's say delta G mu nu equal to 0 always, or even if you put some matter, okay? I just want to make a point here, but we will derive that GR point of view a bit later. You get that solution phi equal to psi, that there is no like anisotropic stress in the FLRW spacetimes. And in GR, this fluctuation, basically, if you have nothing in the vacuum, basically this is just your Newtonian potentials, they are not dynamical. But it's not the situation in modified gravity. So how do we know that? Well, we know it by only looking at perturbed equations of motion. So we start with the scalar fluctuations of this form. And what we do here is two steps. Step number one, find out the second order action around your favorite background, and your background, we fix the background to be close to de Sitter here. Okay. So as I said, we have close to de Sitter, universe is inflating and exit towards matter dominated era. So we are looking at fluctuations around this close to de Sitter stage. And you have these 2 degrees of freedom, phi and psi. But at the end, you get only 1 degree of freedom, which is some combination of these. Okay, so this is the effective degrees of a degree of freedom, which propagates, which is called scalaron. Maybe my pronunciation was not clear before, so let me write it similar to inflaton. Thanks for asking that question. So how do we get that? Let's see how do we get it. So when we do the, let's say we start with the action, right? We want to do second order perturbation. It's easy to do. So the one term you can write is mp square plus 2 f0 r bar. R bar is some background. Second order perturbation of square root of minus v r. It's easy to understand, mp squared. Okay, let me write this clearly. So if you have second order perturbation, you basically have the d4x. So you have the gr term, which is mp square by 2 square root of minus g r. So you have to do the second order variation of this. Then you have the r square term, which also has square root of minus g f0 r square, right? And what is the second order perturbation? You have several terms that appear here. So the one term is second order perturbation of square root of minus g r. Then the remaining part is background. Okay. Then there is f0. Then there is another term, f0, first order perturbation of square root of minus v r bar delta r. That means you vary square root of minus g, you vary one of the Ricci scalar, and remaining is r bar. But you have to vary the other Ricci scalar, which is already here, accounted here. And then there is another term, which is f0 square root of minus g bar. Bar is background, and then you do the second order variation of r. So these are the only terms you can get. So a lot of times studying perturbations scare us because it's too much complicated. But actually, if you follow the steps, you do the second order variation, you do the variation of all the terms. Maybe tomorrow I can just show you in the beginning the mathematical code, how you can do this. If you're interested, maybe I can just show you the for 5 minutes. It can be done very easily if you know matrices and Taylor expansions. And Mathematica has a simple way. If you know how to write matrices in a mathematical code and do the Taylor expansion, you can get everything quite easily done. So let me summarize here. Because I took the overall half factor out, right? So I put, well, there is everywhere f 0 by 2, 2, 2, 2. Yeah, remember I started with f0 by 2. Because I took the overall factor out, I get terms like this. There is another term which I did not write here. The first variation of R and also another first variation of R. You have two Ricci scalars. So it's easily. You look at the terms, you vary two variations, and then all the remaining you do not do variation, you put the background. That's what you do. Okay. Let me write some relations which give you the feeling that at least what you know what's going on, right? So the point is the following: you are doing variation around the background, but you have the equations of motion. Let me write the equations of motion: E mu nu to be 0. Basically, I'm writing the whole piece as some E mu nu. Okay, and if you vary the equations of motion, why are we doing it? We know that at least from the what Luca presented, there is only one degree of freedom, which is propagating. So, but here in this way of representation, this is basically the 1 plus 3 decomposition. So we want to understand what is the propagating degree of freedom. We want to write second order action in that single degree of freedom. To single out what is that degree of freedom, we use the linearized equations of motion, which give us constraints. And these constraints will reduce this whole complicated expression in a very simple form. So to do this, since we are in a regime where R square term is dominant, what does this mean? You have R bar much greater than M square. This is the regime. You can translate into a condition that F0 R bar is much greater than MP square. How do you translate that? It's actually the same condition. You substitute F0 here, and you indeed replicate this same condition. So that means whenever we get terms compared to F0, well, there's two F0 here. Remember, actually, with a factor of 3, this is what we wrote before. Because we are comparing MP square by 2R with F0 R square by 2. And impose this condition, that means we drop everywhere terms depending on MP square, because you are in the regime of R square domination. So if you do this, we write 3 equations here. Maybe, yeah, we write 3 equations. So which will be useful for us. Delta Eij equal to 0. I will put the details in the notes. I thought I could do everything here, but I see the imagination and reality are totally different things. So so delta E0I equal to 0. And let's also see, for example, you have box R equal to M square R is the trace equation, right? If you naively vary this equation, basically you get approximately. And there is also variation of box, but you can do that, but just give you some intuition. So you have ij equation, 0a equation, then yeah, sorry, one is 0 0 equation and 0 I equation. You have three equations. The detailed steps will be there in the notes, but if you combine these three equations, you get two solutions, which tell you, sorry, which gives us the later the picture of a one propagating degree of freedom. So one solution, well, by the way, we apply this approximation, okay? One solution you get is phi plus psi equal to 0, phi equal to minus psi. This is different. If you know in GR, you get two Barton potentials and solve the GR perturbed equation, you get ij equation gives you phi equal to psi. But here, during the inflationary evolution, you are in a modified gravity regime, your Barton potentials satisfy a different relation, not phi equal to psi. But of course, when the inflation ends, you exit the inflationary regime, yes, this phi almost becomes psi, like you know in GR. So this psi and psi has some evolution. So during inflation, at least up to the these approximations, you get phi plus psi is almost 0. Then there is another very interesting relation, that is delta R is 2 R bar psi. I hope I have the equations of motion here. Okay, look, when we perturb this is perturbation of Einstein tensor. You get some bunch of terms in phi and psi. But if you do the perturbation of these, you get delta R, right? You get delta of Ricci scalar. So then if you study the constraint equations, your delta R, the perturbation of the Ricci scalar, is just proportional to the Barton potential multiplied by the R-bar background. I hope you are following it. Please feel free to ask any questions. So the idea is to derive, but we don't have time. But the idea is to understand everything that is coming from equations. We have to read equations, understand what they are giving us. So if you, for example, let me write how delta R, the variation of Ricci scalar, look like. If you apply this constraint, just it gives me simplification. Basically, this constraint, you get it by doing some combination of these equations. And when you apply this constraint, your delta R gives you that 2R bar plus the, okay, I think something like this. So let me, it's not something like this, exactly like this. So 2R bar times uh, ah, okay. So I confuse where to put the brackets. So delta R, after applying 5 plus I equal to 0, will become this expression. But then when you look at the constraint equations, these constraint equations tell you that delta R is nothing but almost psi. What does it mean? You look at that R square term is 4 derivatives, right? But the two derivatives are basically your existing scalar, which cancel the polarization, zeroth order polarization, as Luca explained. The second piece is what propagates. And this constraint tells you that you got rid of two derivatives. Then there is a remanent piece. That remanent is what a propagating degree of freedom, which is you get, you apply these two constraints and plug in here everything. Yeah, similar to that. Yes. Your dynamical degree of freedom is basically the something you write it in a canonical variable that is proportional to psi, and box psi equals 0. So there is a, after applying the constraint equation psi, your Bardeen potential still have dynamics. Those dynamics are the scalar dynamics. Yeah, yeah, exactly. Yeah. So you can do the exercise. The detailed derivation is there, but it's, let me repeat, it's not complicated. Okay, to get your feeling, after you apply this phi plus I equal to 0, your second variation of square root of minus g r just becomes 6a square del psi minus psi prime square. It's so simple expression. So you get a lot of simple expressions and you plug in everything here. And as an end result, you have to do some integration by parts, maybe one or two, if you don't get confused. So you one or two integration by parts and omitting total derivatives land you in the second order action of the following form. Ah, prime is a differentiation with respect to conformal time. So we are working in conformal time. So now when you compute the second order action, maybe I can write it here. That's clear. Sorry, I'm maybe causing you trouble. Uh, of d4x square root of minus g bar sum u box q. What is u? Let me call it as u tilde in my notation. So yeah, okay. Yeah. Okay, yeah, that's true. Your second order action and u tilde is square root of 6 by f0 r bar u, where u is 2 f0 r bar psi, which you can notice it's nothing but delta r. So, well, proportional to delta r with some factors of f0 r bar. So that's, you end up with a variable which has dynamics because there's a box operator. And these dynamics are encoded in psi. Now, what do we do with this? What is the goal? The goal is you study fluctuation and you compute second order action and you compute what are the fluctuations, how the fluctuations look like, and how the fluctuations are behaving during the inflationary expansion. And let's say if the fluctuations just, they will be there, but then completely go away, then there will be nothing left. Or if the fluctuations leave some imprint in this geometry, in the inflationary geometry. And that's the goal we want to see. And these are geometric fluctuations. It's important to understand these geometric fluctuations, if they leave an imprint, that means they leave the space-time geometry with a lot of inhomogeneities. And whatever the matter that forms later due to the decay of this field, because these are the large scale fluctuations, and these large scale fluctuations create the geometry in which the whole evolution of universe gets encoded. So this is gravity, completely gravity. We should not think like this is some matter field there in the early universe. This is creating a geometry, and this is part of gravity. Should not think of a particle. Scalaron is not a particle. Later, maybe tomorrow we go to the Einstein frame. We write this same Lagrangian with Einstein-Hilbert term with some scalar field. But we should never think that this scalar field is some matter, because there is a common misconception is that you have gravity and you have matter, but this matter is creating a new geometry, and this matter is influencing creating fluctuations which will leave imprint, and that's what we observe now, is remembrance of things of the past which are left and we are observing now, the memories, the gravitational memories, if you think that way. This is important because most of the time we get lost if we do not extract physics from the equations. Okay, I haven't worked out the equations, what gives the geometry, so I will show you that. Okay, so just as a message, as a driving force for you to look forward to tomorrow. So what we do, but well, I still have a few minutes. Okay, I will go on, so don't worry. So again, we are in the de Sitter. What is the nature of de Sitter space-time? De Sitter space-time gives us a horizon. So let's try to write this. So if you have a metric, this is de Sitter metric, right? When your h is constant, but you understand the real picture is a bit more involved terms, but still this understanding help us to achieve something. So if you want to see the maximum distance that a light can reach at any given moment of time, this creates a boundary by length scale. So let's say if you think that this is basically isotropic space-time, right? So you think of it like a sphere, and this sphere is expanding with conditions, right? It is expanding. You assume that the time is running minus infinity to infinity, and you're assuming your Hubble parameter is positive because in the de Sitter space. So we define an arrow of time, which is something similar to what we do in quantum field theory as well. Luca mentioned it. So in quantum field theory, we define an arrow of time. So you define an arrow of time. You say that there is a expansion of universe which is created by growth of the scale factor. As the scale factor grow, the amount, the region of space-time you can see, an observer can see, shrinks. Okay, and this is what it is, and this is it's a horizon. Horizon is basically where null geodesics ends, and you cannot see beyond that. So we are looking at metric fluctuations evolving in such a geometry. And when fluctuations, which is a field, meets the horizon, quantum mechanics kicks in. So this is, well, in the early stage of evolution. So during inflation, universe is very small. There will be quantum fluctuations. This is what normally we all know. This is the picture we present. But think of it this way. Because there is a horizon and there is a fluctuation, and this fluctuation can evolve and hit the horizon, and the wavelength of the fluctuation normally, okay, when you look at fluctuation, is basically we talk in terms of wave numbers and wavelengths. There are two ways to there is a co-moving wave number and a physical wave number, because you see your space is expanding, but if you want, there is a physical wavelengths which are basically A times lambda, and lambda is a co-moving wavelength. And physical picture is K times A. So there is a concept of co-moving and physical, but whatever it is, it's just different perspective of seeing what is happening during this expansion. Either if you talk about physical wavelength, that means the boundary is fixed, whatever inside is changing, kind of redshifting. And other way, your boundary is changing. So it's just two perspectives of understanding what is happening. And because Hawking told us, whenever you see horizon, you will see quantum fluctuations. So this was the aftermath of original Hawking paper, and there was Gibbon's Hawking paper about understanding de Sitter space. And surely that has after evolved into understanding of inflationary quantum fluctuations. So I have 10 minutes. Oh, well, it's relative. So that means we have to understand quantization of this variable u tilde, which is proportional to the Barton potential. Well, remember that R bar is nearly constant during inflation. Okay, then we meet with a complication. The complication is the following. When you say quantum, here we are talking about gravity, right? Because it's a space-time which is expanding. How do you think about quantum, something quantum evolving in expanding space-time? So there's no easy way to do it, but let's try. We closely observe how this kinetic term look like. So in the conformal time, put an overall minus sign here. So basically, it's just a box operator written in conformal time. And basically, you have this friction term. And this is just a spatial derivative because your psi is function of space and time, conformal time. Okay. Your box operator will look like this. I will try to give you a schematic picture of this, but tomorrow we will derive this. This is really the crux of quantum mechanics and gravity acting together. Then you can ask a question, why quantum mechanics? It's quantum field theory, right? Quantum field theory is built upon just replicating what how the quantum mechanics is constructed. It's just you apply it, you replace Hilbert space with Fock space and momenta with the conjugate momenta of the fields. So at the end of the day, is something relativistic quantum mechanics is nothing but quantum field theory. So don't get confused with this when I say quantum mechanics and GR. So the trick is basically you have square root of minus g. What is square root of minus g bar? I'm going slow here. Maybe it's, for a lot of people, maybe trivial, but please let me know if you want me to speed it up. Square root of minus g is a power 4 in conformal time. And by the way, I missed a factor here. There's a factor of 1 over a square. So this becomes half square root a power 4 d4x u tilde, well, this is 1 over a square, right? Minus d tau square minus 2h d tau plus ds square u tilde. And a square is cancelled and you have a square. And it is tempting to rethink that, think that, okay, you can basically rescale u, okay, with the scale factor. You absorb, you define a new variable. I'm almost done, just a couple of more minutes. I'm talking about scale invariance. So just so you define a new variable v, which is a times u tilde, and this variable, this definition makes a magic. I specifically write the time and spatial integration, and v looks like minus yeah. Well, there is a new guy entered here. What is z? Z is something proportional to a. There are some factors of a. So z double prime by z actually in the de Sitter approximation looks 2 by tau square. Uh, yeah. But if you look at this Lagrangian, first of all, there is no square root of minus g. It's taken care of by this redefinition. Okay, so it is absorbed. Then we wrote it here. This looks like just a box operator in the flat space time. So you forget about this scale factor. So you just have like a box operator this for this variable v, and then you have a mass term. So this is nothing but some field living in a flat space time with some mass term and which is time dependent. So that means we got rid of gravity and looking at this redefined field as something fluctuating, and the mass term is exactly the effect of this redefinition. So you remove gravity and uh, place the effect in the as a time dependent mass. But there is something issue here. If you look at this, it looks like box plus m square. Remember our convention minus plus plus. The action is box minus m square is your standard Klein Gordon field. But this does not look like a field with a positive mass term. It's a negative mass term, negative mass square. So the mass square is minus z double prime by z, which is approximately, if you think this field is a kind of continuous limit of a collection of infinitely many inverse harmonic oscillators. Normally in physics, we see only harmonic oscillators, but not inverse harmonic oscillator. But the step of removing gravity and write it as some canonical field living in a flat space time and some mass term. So this is a gravitational effect is giving an inverse harmonic oscillator. This is a new phenomenon, and this is what something totally new that gravity is telling us. And gravity, if you combine gravity and quantum mechanics, you get not normal oscillators, but inverse harmonic oscillators. We'll stop here and understand how this inverse harmonic oscillator field is leaving an imprint in the CMB, which we are seeing amazingly which we detected. That's incredible. We are seeing the relics of early universe cosmology. Thank you very much.